Welcome everybody, and it is an extreme pleasure to introduce my half brother in mathematics, Emilio Franco from Universidad Autónoma de Madrid, who is going to talk about branes on the singular locus of the Hitchin system. Second part.
Second part.
Thank you.
Well, thanks for the invitation, Marina, and thanks everybody for your attention. I'm going to talk about some phenomena occurring in the Hitchin system. The Hitchin system is related to the modular space of Higgs bundles. For the purpose of today, I will consider Higgs bundles of rank 2, degree 0, over a smooth projected curve of genus 2. Okay, I'm gonna fix the genus to be 2, and the rank to be 2, and the degree to be 0, which is one of the simplest cases, which is still not trivial, and where we can do geometry in a very simplified way, just for the purpose of the presentation, so you can understand better what is the essence of our work. Well, let's go quick. The modular space of Higgs bundles classifies Higgs bundles, which are pairs of rank 2 vector bundles in this case, and phi is a Higgs field, so it's an endomorphism twisted by the canonical method of our smooth projected curve. See, if we consider another modular space, which is the modular space of flat connections, flat rank 2 connections on C connections. One has that there exist after work of Hitchin and Donaldson in this rank 2 case, so there are many more people involved in the arbitrary rank case, but for this rank 2 case, Hitchin and Donaldson show that there exists that inferiormorphism between these two modular spaces, so their underlying manifold is the same, the underlying variety is the same. In this case, one can see that this comes equipped with a complex structure, which I, which comes from the curve, and this comes with another complex structure, J, which comes from the group GL2C, the structure group of all these Higgs bundles and these flat connections. So we have here, we can interpret this diffeomorphism as having two complex structures on the same underlying manifold, and in fact, one can show that there exists a much richer geometry, which is a hyperkähler structure over this modular space. So indeed, one can equip this with a hyperkähler structure. Which, as you know, is a triple of complex structures satisfying the quaternionic relation. So meaning that This is precisely Ij. And for each complex structure, one can build a Keller form acting on our metric, on one of the entrants of our metric with the corresponding complex structures, which are Keller forms, a triple of Keller forms. And in fact, one can build homomorphic symplectic forms. For example, one can consider omega j plus I omega k, little omega j plus I little omega k. This is a holomorphic symplectic for the complex structure I. Okay, one can equip our model space of Higgs bundles with a holomorphic symplectic form. So it's holomorphic symplectic. So in this context, one can study. So it's a model space. The model space of Higgs bundles is a model space with an extremely rich geometry and has been used a lot in mathematical physics in order to produce some physical theories which come equipped with a certain duality. One of them is what we call mirror symmetry. In this context, Kapustin and Witten, they make use of this hyperkeller structure of the model space to promote mirror symmetry to a hyperkeller version of it. So mirror symmetry usually provides an equivalence of categories of something that we call A-branes and B-branes. These A-branes depend on the symplectic structure of our framework. Those are equipped on. So we have a mirror manifold X check, and A-branes are Lagrangian subvarieties of X equipped with a flat bundle supported on all Lagrangian subvariety. While A-branes are holomorphic subvarieties of my mirror manifold equipped with a holomorphic vector bundle. So as I was saying, Kapustin and Witten propose sort of a hyperkeller version of this correspondence. So they were talking about BAA branes, a duality between BAA branes on the modular space of its bundles for certain group and BBB branes on the modular space of its bundles for the Langlands dual group. In this case, those would be complex Lagrangian subvarieties for omega I on our modular space of bundles equipped with well, I will set this complex Lagrangian subvariety and it comes with a flat bundle supported on this set. Here we will consider three holomorphic or hyperkähler, sorry, hyperkähler subvarieties on the dual space equipped with a hyperkähler bundle. So meaning that this comes with a connection whose curvature is 1,1 for I, J, and K. Okay. So we have promoted this correspondence between B branes and A branes to BAA and BBB branes. If you think about these objects, they are ultimately sheaves equipped with more structure. So part of the conjecture is that the underlying sheaves between, the underlying sheaf of a BAA brane will be sent to by a Fourier-Mukai transform to the underlying sheaf of my dual BAA brane. So I would introduce something which is called Fourier-Mukai. I will later on I will explain what it is, and I will give more detail. But there is some correspondence between sheaves. This Fourier-Mukai transform is a correspondence between sheaves, which sends the underlying sheaf of a BAA to the underlying sheaf of my dual of the dual BBB. And as I said, this Fourier-Mukai transform is a proper equivalence of categories between categories of sheaves, which I will explain in more detail later on. Okay. So this hyperkähler structure is one of the main structures of the modular space of its bundles, but there are more. We have more geometric structure. It's an extremely rich geometric object. The other important structure is a vibration, which we call the Hitchin map, whose fibers are complex Lagrangian subvarieties. So the Hitchin system is the data of a morphism from our moduli space of Higgs bundles of rank 2 to a vector space, which is nothing but the space of sections of my canonical bundle plus the space of sections of the square of my canonical bundle. The morphism is realized by sending a Higgs bundle to the trace of the Higgs field and the determinant of the Higgs field. And out of an element, which is actually a pair of sections of powers of the canonical bundle, one can build the so-called spectral curve. How? Well, we consider the total space of the canonical bundle, which comes naturally equipped with a morphism to or curve, or smooth projected curves, in this case of genus 2. Here, I will consider the pullback of my canonical bundle, which comes naturally equipped with a tautological section. Sending, well, the fiber, the point, a point in the total space is actually a fiber of the canonical bundle to the actual fiber over the corresponding point. Okay. And for this B, one can build a sigma B, a section of this form. This is a section of the square, the pullback of the square of the canonical bundle, and we will define this CB as the vanishing locus of this section. Okay, and we know that, well, my CB lives inside this total space. This is included here, so it comes equipped with a morphism to C, which is 2 to 1. 2 to 1 morphism given by the restriction of this projection to the curve, and it's 2 to 1. You can say it's 2 to 1 because it's a rank 2. Well, it's a degree 2 polynomial. There are solutions of a degree 2 polynomial. Okay. Also, one can show very easily that the fiber over the point corresponding to B is actually the compactified Jacobian of CB. Compactified Jacobian meaning that it classifies torsion-free sheaves on CB. And this isomorphism that we have here is realized by sending a torsion-free sheaf to its pullback. This gives you, since we are, since this is a 2 to 1 map, this gives us a rank 2 vertical bundle on C, and the corresponding Higgs field is given by the push forward of the morphism that one obtains by tensorizing by this tautological section. So this sends F to F tensor K. This gives this field from E to E tensor K by the projection formula. So this gives us a Higgs field. So we have a description of the fibers. There are these compactified Jacobians. They are compact by a result of Simpson, because we're classifying things, well, sheaves over a projective variety. So we'll get a projective variety again. Whenever if CV is smooth, this compactified Jacobian actually is the Jacobian, but when CV is singular, the Jacobian is not compact. Actually, it's not compact, and this is included in this compactified Jacobian. It's just an open subset. One can show actually is this smooth locus. Of it. The Jacobian is the smooth locus. That's what I mean. And one can show that
what is in the compactification of the Jacobian that is not in the Jacobian?
I will go through that specifically. So these fibers are Lagrangian for this big omega I. Okay, this complex structure of the moduli specification. This complex holomorphic symplectic form. Okay, so let's focus on singular spectral curves, and let's describe in this case, since I'm fixing the genus to be 2, and of course the rank to be 2, one can have a very explicit description of this set of spectral curves. Okay. So first of all, let's compute singular spectral curve. Know that we're working with this rank 2 case. Oh, sorry, genus 2 case. So first of all, in order to compute the genus of CV, what we do, we recall that CV belongs to this local system, to C. So we know that two GCB minus 2, this is actually CV intersected, self-intersected with CV. This is for the self-intersection of our curve, so this is for G minus 2, 4 times G minus 2. In this genus 2K, that give us that GCB, this GCB is 5. Okay. This is good because B, the dimension of B, if we recall, is it's hk plus h not k squared. This is 2 plus 3, right? So it matches. We consider C to be singular. We consider its normalization. There is some bounds for the genus of this normalization. So the most extreme case is when when this morphism, the decomposition, this gives us a composed morphism. This is 1 to 1 is the normalization. This is 2 to 1, so this is 2 to 1. So if we have a 2 to 1 morphism, and the extreme case is when this morphism is unramified. Well, we know that Kc is actually K sigma b. Therefore, we have that 4g minus 4, 4g sigma b minus 4 is actually 2g minus 2. This gives us that the extreme case when GB is unramified, it has to be 3. Okay? And we have a genus 2 curve here, so this normalization is from maximum, this is more than 3, so this is the normalization. This is 5, and this is more than 3. So the number of singularities, can be 1, well, 0, of course, 0, 1, or 2 at maximum in this very simple case. Okay, so one can stratify. This gives us stratification of the Hitchin base in terms of B0, the smooth part, well, yeah, deeper strata, B2, B1, and B0. You have a stratum of very similar cases, curves with singularities of length 2, singularities of length no more than 1, and smooth curves. Okay, so one can stratify by this number of singularities in this very simple case, genus 2 and rank 2. Okay. Okay, so let's study the case of just one singularity. We'll focus here. So if we consider the normalization, we have said that G sigma is 4, GCB is 5. One can consider two morphisms associated with this normalization. The first one is taking pullback under this normalization morphism. So the pullback, which I will denote by n hat, goes from the Jacobian of CB through the Jacobian of sigma b, and the other morphism is taking the push forward. Jacobian of sigma b to the -1. So here you can consider the same degree. I will write degree 0, but usually we have to consider any degrees. But yeah, for the purpose of this presentation, if we take here a line bundle, one can consider the push forward under normalization. That gives us another torsion-free sheaves or a sheave over CB. And in this case, it's not a line bundle. We're going to have a very explicit description of these guys. So they're sort of dual, these two morphisms. But there is a problem. The problem here is that these do not extend to the whole complex grade Jacobian. We have to restrict to an open subset, the smooth locus gate. Since we're working with dualities, most of these constructions are done using this dual set of dual pair of morphisms, and one wish to construct some morphism that extend to the whole compact hydrocarbon. As I said, this is not possible. It does not extend to compact Jacobian. So instead of that, we're going to consider another moduli space, classifying things, sheaves, well, something very close to these sheaves. We call them parabolic modules. Were defined by Musa-Bosle. Parabolic modules are given by pairs of line bundles, line bundle over the normalization, and B. Oh, if this is the point B, the pre-image are gonna be called B plus and B minus, and B is gonna be a subspace of the restriction to B plus of L and the restriction to B minus of L. Okay. And by definition, this comes by construction. This comes actually with a morphism to the whole Jacobian of sigma. We just forget about the B. Okay.
I have a question. Is this the only possibility you have for singularity? Is it not possible to have a cusp? So that
yeah, we can have cusp. Here I'm restricting to nodal curves. Well, length 1 in this case will imply nodal, but one singular point of length 1, one singular nodal point, I would say.
And in fact, I think that you are checking with this stratification. You are stratifying by the genus of the normalization, right? Because
Yes.
you would have
Also,
a
yeah.
variable singular point and genus of the normalization to be 5, right?
Also, but the length, if you consider the length of the singular divisor, that corresponds to the genus of the normalization. Not the number of points, but the number of points with the appropriate multiplicity. But so yeah, the length. Yeah. Okay, so we have defined this modular space of parabolic modules. They're just pairs of these line bundles over the normalization, and a subspace of this this C2. This has rank 2 vector space. Okay, so we see that basically the collection of all these subspaces, this gives us a P1. So this is we represent Chuck bar like that. This P mod actually is a P1 vibration. The fibers are P1s. It's a P1 vibration over the Jacobian of the normalization. Okay. So how this relates to the actual compactified Jacobian through something we call Hecke transform. We're going to consider a third morphism called so from the modular space of parabolic modules to the compactified Jacobian. We're going to send this pair B, LB to the following shortest stack sequence. We're going to consider the push forward of L, and now we're going to consider a morphism from this push forward to LB plus LB minus quotient by this B. And this gives us a kernel F. Actually, this F is the Hecke transform. For this pair. So we're going to send this pair to this F. Okay. This is when B is not LB plus nor LB minus. This gives us an identification of the fiber of over B plus and the fiber over B minus, so we get a line bundle on CV. Okay. But when
You're seeing the guy on the right as a skyscraper seed, right? You're taking
it's a
the
skyscraper,
kernel,
yeah.
the skyscraper, and then you're taking the the kernel of that.
Yeah. You restrict, L tensor the skyscraper, L tensor the other skyscraper, and then the quotient. Exactly. Yeah. So when the subspace is neither of those two, well, we have an identification, we get a line bundle. When B is actually LB plus, we have an identification of the Hecke transform. So So the Hecke, we have Hecke of L and B equal LB plus, with the Hecke of L prime being B plus minus B minus as a line bundle, and B being L prime restricted to B minus. Okay, so we get an identification. So here we have the zero section, but also we have the infinity section. So we have the zero section and the infinity section. And this morphism, what it does is twisting and gluing. Okay, so we get the jack CV we glue these P1s over the 2 points that are shifted. These 2 points are shifted by this line bundle here. And the thing is that for each point, over each point of this zero section glued to the infinity section, there are 2 points of the P1, 1 infinity point and 1 0 point. Okay. So there's no way of producing a morphism. So it's a very beautiful picture. There's no way to producing a morphism to Jack sigma, but we have a copy of Jack sigma here, which this is just the image of Jack sigma under this new check morphism. Okay, this is the singular locus. So corollary singularities of this compactified Jacobian in this case is actually the image of mu check. So all these line torsion free sheaves obtained by push forward on the normalization of the Jacobian. The -1, okay, so degree -1. Okay, so we have a description of this modular space of this singular locus of our compactified Jacobian. Now we can understand. Well, let's go back to our stratification.
There is a missing part, right? It's singular, the singular locus of the compactified Jacobian.
Of the compactified Jacobian, yeah.
I don't think if there is
The other part is smooth.
This is smooth.
And well, you can see written this description very nicely here. It's when you take out all this zero section, and well, it's the Jacobian is a copy of C star, and the Jacobian of the normalization. And in this case, from that, you can choose whether to go to the infinity section or the zero section, but there are morphisms, the Jacobian of the normalization. There are 2 morphisms actually. Okay. But when you glue these 2 sections, the infinity section and the zero section, twisted by this line bundle, there is no way you can have a morphism to the whole, from the whole compactified Jacobian to the Jacobian of the normalization. Oh yeah, before finishing here, if we consider, well, I will leave it here. If we consider so this is a P1. So I will. This is the morphism mu dot of the morphism from P mod to the Jacobian of the normalization. Obviously, the fibers are P1s, and observe that when you restrict to one of these fibers, there's no way you glue. I mean, this is still a P1. Okay? This time is inside the Jacobian, the compactified Jacobian. Because this morphism, yeah, you go from, this is the tau morphism. But if you restrict to one of these guys, you actually get one of these guys. Okay, but there is no possible identification. You will identify it with another P1, but you're just selecting one. So this is just to give you an isomorphism. This is just a close embedding. Okay, so when you restrict to a fiber, you get a close embedding. Okay, that would be important later on. I forgot to mention before erasing. So let's go back to this stratification by the number of singularities, the correct number of singularities. We have the smooth, we have we have B, we have B1, we have B2, and one can build using actually the singular locus. So it's image of the Jacobian of the copied by Jacobian as a fiber, integrating all this. This gives us a symmetrical system of the whole Hitchin system. And one can show that this is a holomorphic symplectic subvariety. So the holomorphic symplectic form restrict giving holomorphic symplectic form on this subvariety. And also, well, one can do the same. In this case, I haven't said much about the case of singularities of multiplicity 2, but one can also consider the push forward of the normalization. This is, in this case, this is something of dimension 3, because in this case the genus of the normalization is 3. So this gives us something smaller. This is something of dimension 4. And also this M2 is a symmetrical system. And in this case, one can show that it's a hyperkähler variety because it comes from, well, the image of the moduli space of rank 1 Higgs bundles to sorry. Let me check to this the moduli space of rank 2 over C, right? This is a hyperkähler morphism, so we get the image, which is M2. It's a hyperkähler subvariety. This is, one could think that perhaps this M1 is also a hyperkähler, but Hitchin proved that M1 is not hyperkähler. Not as hyperkähler subvariety. However, in certain limit, Gaiotto more native show that, well, they conjecture that in a certain limit, this becomes a hyperkiller for the same flat, or for an analog for the same flat. For the same flat, an analog. Okay. Okay, so the objective of our work is to construct a Lagrangian subvariety, a BAA brane, whose Fourier-Mukai transform lies on this M1. Okay, and this is what we did. For that, we have to focus on studying Fourier-Mukai transforms over the singular locus. So let me give you a brief summary of what is this killer. Oh, sorry, what is this Fourier-Mukai transform? Well, in full generality, the Fourier-Mukai transform was defined by Mukai. In this case, that was done by Arinkin. So Arinkin constructed a Poincare sheaf over the product of the compactified Jacobian with itself and one can build an equivalence of categories from the derived category of this compactified Jacobian to itself. Just by sending a complex here to the pullback under P of this complex, tensorized by the Poincare sheaf, and then taking the push forward. Everything is derived, so I should be using the appropriate derived functors. And I can show that this is an equivalence of categories. Okay. And what we did with Johannes, Hanson, and Oliveira, we studied sheaves, the Fourier-Mukai transform of sheaves that comes from the push forward of this morphism we call that we have from the Jacobian of the normalization to the Jacobian, the compactified Jacobian, and it actually lies over the singular locus. So we study the sheaves supported in the singular locus. What we found is this formula. So this is over check bar, let's say CV, okay? We found that this is given by the push forward of tau, tensor by, we have to go to P mod. We take the dualization sheaf of P mod, we take some bundle that I won't talk about that today, coming from the Jacobian of the curve, and then we have to tensor well, we have to testify the Fourier-Mukai that one can build over the smooth Jacobian of the normalization. Okay. So note that when we transform a line bundle, if E is a line bundle, so if we take here a line bundle L, we take here a line bundle L of degree 0. So the classical, this in classical Fourier-Mukai transform, this gives us the skyscraper supported on the actual line bundle. So in this case, this is a skyscraper. Oh, sorry, this is the pullback. The pullback under Newton, right? So this Newton, well, you have to go from here to the T mod, and then they push forward to the checker. So we get here, we get 1/2 T mod. And we tensor by the skyscraper over the fiber of the corresponding, this is a P1, okay? This is a skyscraper over the P1. And well, it would be trivial, so I won't care about that. But this guy actually, well, it was a P1 vibration, so the omega is it's restricted to the fibers is omega is O minus 2. So we'll get here O minus 1 over this fiber, and as I say, this is just a close embedding here, so we'll get O1 minus 1 as a fiber, well, over the fiber, the corresponding fiber of this guy. So integrating all these, we were able to build brain, a BAA brain, whose restriction to each of the fibers is this P1. Just a conclusion. Such that this BAA intersected with the corresponding complexified Jacobian, so the corresponding Hitchin fiber is precisely is O1 minus 1, and well, by construction, we know for sure that the Fourier-Mukai transform will be supported, will be given by this guy, the inverse of this BAA intersected with this Jacobian is precisely this new check of this line bundle. So we get BAA, the dual of this will be supported on this M1, okay, which is not a hypercurvature number. Okay, so we're still trying to understand what this all mean. But if we go back to this Gayotto-Ornitsky conjecture, actually it seems that in order to have this duality of brain, it's enough to have some sort of hypercurvature behavior in this certain limit. Okay. Of course, here we're working with the moduli space we're working with the category of coherent sheaves. The work on Langlands, to the geometric Langlands program, suggests that one should be studying this Kapustin-Witten mirror symmetry in the context of stacks and in the context of incoherent sheaves. Perhaps, we still don't know, but perhaps this would be could be put in this framework precisely. But yeah, this is still work in progress. Okay? And that would be all I wanted to talk to you about. Thanks.
Thank you. Is there any question?
Can you say some words about how you prove this?
At this point, fiber-wise, we have this fiber-wise Fourier-Mukai form, and then we know how to restrict to any fiber. So, okay, just the inverse Fourier-Mukai form would be given by what you put here. So,
no, what I'm saying is, how did you prove that formula?
Well, yeah, that took a lot of time. Yeah, you have to study. You have to study the construction of the Poincare sheaf by Arinkin, restrict to the singular locus, then have a good control of this Poincare sheaf restricted to the singular locus. Express this restriction of this Poincare sheaf to the singular locus in terms of the Poincare sheaf of the normalization, and there you go.
I see.
And then after you have this description of this restriction of the Poincare sheaf, singular locus, in terms of this other Poincare sheaf, other smooth Poincare sheaf of the normalization, it's just a bunch of base chains in this derived category. It's not. The hardest part is the description of the sheaf, of the Poincare sheaf. That was long. That took us a lot of time.
More questions? Just to mention, I mean, you explained it for genus 2, rank 2, so I guess that is valid for any
genus,
and
any rank. Yeah. But yeah, for the purpose of the presentation, I really love the rank case.
Yeah.
You have a good amount of difficulties, technicalities, and also it's much simpler than the other case.
And with respect to what Enrique was asking, then in that case, in more general case, you deal with also cusps or?
No, we restrict to nodal curves, which would be the open subset of this stratification. So as long as you have something on the open subset, which transforms to something on M1, there you go.
Okay.
You'll get something supported on M1.
So no, that's enough. That's the thing.
Yeah, exactly. It's enough.
Like
Yeah.
the model is built
I know. Yeah, we do that for nodal curves. Also here in this Fourier-Mukai result is done for nodal. But in this rank 2 case as well, yeah, M1 can only be nodal.
Okay. So if there are no more questions, let's thank the speaker again.